Hi and hello. I'll give a talk today about ZKAPs, and we're going to talk about how to use zero-knowledge proofs of payment-based access to your application. Hi, I'm Anna Kaplan. I am a security researcher and a graduate student. I work for Lease Authority and I study at the University of Munich, and I'm excited to be here. So ZKAPs. This is going to be a very, let's say, practical approach, and we're going to look at a practical protocol. So I hope you like it. I'm going to show you technicalities as well, but we're not going to use a crazy zk-SNAR construction, but just a very kind of simple, let's say, discrete logarithm equivalence proof. I hope you're as excited as I am. Okay, so what are we going to tackle today? Okay, that works now. We are going to look first at the use case and think about like why, and like I'm going to explain to you what was actually the problem we wanted to solve. Because this is the case, right? We have this really cool constructions with zero knowledge proofs, but then like people have use cases and they really want to use them, and it's somehow the problem is how to bring those together. So I'm going to tell you about the use case we had, that Lease Authority had, and then I'm going to talk about, I'm going to go a little deeper into the use case, which is actually a cloud storage solution called private storage. And then another thing came up, another private thing, privacy pass, which another team and another group did, and which then Lease Authority adapted for the use case and used the underlying technologies and privacy paths to use for their cloud storage solution and their problem. So I'm going to explain, this is ZKAPs, and I'm going to explain ZKAPs then. And then we're going to think about extensions, or more, I want to motivate you to use ZKAPs or these ideas in for your problems and your use cases. Okay, let's dive in. So what happened was, I'm now like in the top. I hope that's all right. So what happened was that Lease Authority, oops, I cannot, like, I'm so sorry, I cannot put my window down. Somehow this is not working. Okay, so Lease Authority built a private cloud storage solution. The idea is that you have a cloud storage, it's private though, and it's the focus is really on the privacy. So there's client-side encryption and the cipher, like it's your text is encrypted, and it's like getting like separated and put like somewhere else, and there is a grid, and it's not ACL, there's no user accounts. It's based on capabilities, so it's like a really like privacy focused solution. So this was the use case. The problem was though that to use that you had to pay, right? Like some point a company needs to make money, so the customers need to pay the company, and for that Lease Authority used Stripe and Chargebee as partners, and as a customer, you had to provide your name and your email address and location and transaction data and all of this data, and all of this was shared to Stripe and Chargebee. So actually, like all personal data was like, yeah, basically like all your personal data was collected for the payments. And as a privacy-focused company, this is not something that you want. Just to like put it all together and summarize it again, the problem was really like just how to separate this accounting step from providing the service step. So in the top, you see that like a customer, he pays with credit card and all of this gets processed, sent to the accounting, and accounting is like saying, okay, this person paid, so you can provide the service. And the problem was we didn't want to do that. So this is in the bottom chart kind of, and this is where the ZKAPs came in. And this is where we use ZKAPs, the zero knowledge access passes. The idea is that like still this like chain goes on kind of, but then the accounting step, what happens is that such passes get sent to the user, and then the user can redeem those access passes to get the service, to actually get the service. So the service provider doesn't know who the customer is, which is something that Lease Authority wanted. So I think the high-level idea is explained now quite well, hopefully. And just to give you like the outcome already, so yeah, there was the cloud storage solution before was called Simple Secure Storage Service by Lease Authority. And Lease Authority came together with another privacy-focused VPN provider, not another, but a which is called Private Internet Access. And they announced private storage, which then used the zero-knowledge access passes that I'm talking about. So you can absolutely check out private storage where those are implemented. Cool. Okay, so how did the, like, how come, okay, this is better. Not right, no, okay. So how come that like the zero-knowledge access passes actually got to be used? There was another work, which is called Privacy Pass, which is work by Alex Davidson, Ian Goldberg, Nick Sullivan, George Tenkasi, and Filippo Valzorda from 2018. And this work was done by Cloudflare. And Cloudflare had another problem they wanted to solve, actually. So the problem was arising because of these amazing things that you see there. Everybody knows that's a CAPTCHA, right? The problem is basically that, as like for Cloudflare, Cloudflare needed to prevent malicious attacks, common spam or SQL attacks from the web. And Cloudflare did that through IP reputation assessment. And to do that, you need to actually use CAPTCHAs too. Like this is kind of the solution that people use, right? How to know if it's a good IP address. You want to check if it's a human. And as a Tor user, I think you've seen those quite some time. So yeah, and this was kind of a problem. But then again, if you use a privacy-focused solution like Tor browser, you have to solve all those CAPTCHAs all the time and prove that you have a good IP address. So the idea was to bring something to people where they have like a pass, they can do it once and they don't have to do it all the time, because otherwise they'll look like this, like because they sometimes cannot solve the CAPTCHA, right? Like this is basically me all the time. Anyways, but this was the idea. And now I'm going to talk about the background of privacy passes. So again, the idea, right? Like you want to say that like you are human, but you don't want to do it all over, so you get a pass. The idea is based actually on a solution by Chaum from 1983, which is called eCache. And the idea there is that you have a token and you blind it with a value, and then you get a blind signature from the service. So in the end, the issuance and the redemption are not linkable because you have this blind signature and you can like later pass it on. So as you see, it's like 1983. I'm not sure how how much you know, but I think like fast crypto was not there yet. So what happened was that after Real Crypto 2016, kind of these ideas got merged, and it was like kind of the question was how to actually apply this idea of blinded signatures to maybe not always solve CAPTCHAs. And Filippo and George came up with the first specification to get this like blinded token, and so get that signed and all of this, and then be redeemed later. So that those are unlinkable to Cloudflare. But as I mentioned before, 1980s crypto was not very fast. It's actually kind of slow, and this was not working. So at PATS in 2016, Alex came on as well, and they asked for help. And then Monet mentioned then EC OPRFs. OPRFs are oblivious pseudo-random functions. So you can think about them like as PRFs with like some kind of blinding factor as well. They're based on elliptic curves. And what then happened is that George came up with a batch solution, which is also like for verified oblivious pseudo-random functions with redemption, batching them also to get more efficiency in the end. You can think about the difference like between VOPRFs and eCache. eCache is publicly verifiable, whereas VOPRFs are only verifiable in the redemption phase by the issuer. So this is kind of the idea, and also I'm going to show you how this works, but still, this is kind of the idea, going from this cache idea to elliptic curve VO-PRFs. Okay, so this was the group background on privacy paths. And you see already, like, okay, you have this idea of like you want to provide a service later, you have to do something before, and then you get passes. This is exactly what the least authority then adopted. Just to give you the general idea for eCache, so you have this token here, we blind it, we send it with the solved captcha to the fairy, because we want to have some service from the fairy, apparently, which is a magical package. The fairy then signs it in a blind way, and we can unblind it and then later send this to the fairy kind of in the redemption phase to get our magical service. So where are zero knowledge proofs then used, right? In the construction for the ECV-OPRFs, DLAC is used. So basically you just show that two discrete logarithms, like they're equivalent, like they, so you basically just show that. You can just think of that as basically a Schnorr construction. So this is where zero knowledge proofs actually come into play. Okay, just for to put the privacy paths chapter all together. So privacy paths now exists as an extension for Firefox and Chrome, and other ideas where this could be used is anonymous session resumption for TLS, or to have some code mechanism like referral, or if you just want to prove I don't know, a single bet something's true or not, and then you can use that. Okay, cool. Let's dive into ZKAPs now. So again, this is kind of the problem, right? Paying somewhere, but wanting a service from something else. Pass. This is what I want to hopefully give to you, that this problem can be solved. This is our problem. And as I said, we'll have some token. We can have more tokens. Actually, we can have a lot of them. I mean, a lot. Yeah, okay, this is not allowed. Hoarding is not allowed in terms of COVID. I needed to bring in a Corona joke. I mean, this conference was put online, so yeah. Anyways, so we have a batch of tokens, but I'm going to show you the protocol 1. So this slide you have already seen. This is kind of the high-level idea. How does this actually work? We're going to look at the issuance first. What is going to happen with our rockstar? So what happens is actually the rockstar selects some random values, which are actually then hashed to the elliptic curve, which gets him the tokens, TI, the big TIs. He also selects a blinding factor, with which he then can blind his tokens. So here it's just, I just showed you, I just put 3 on there, but you get the idea. For privacy paths, I'll just cap this metaphor. You bring your solved captcha. For ZKAPs, we actually check with the provider that you paid, but just in the issuance phase. So not in redemption phase, right? So this is kind of the separation idea. What then happens is that the fairy, in this case us, at least authority, checks that captcha or the payment process and calculates a DLAC proof for the signature. And there's also some other value publicly put up before. And so the fairy or the server then blindly signs those blinded tokens that you send it, and sends over the DLAC. And the rockstar can then unblind these values, stores the TIs and the NIs, and checks, of course, first the DLAC. This is for the issuance phase. This is what happens in the issuance phase. For the redemption phase, what we do is actually we have some request data, which is just a bunch of data like an HTTP request and stuff like that. and the rockstar, the user in this case, has to generate a shared key. This is the SH key thing, which is just a hash of an unspent token. So this is the TU and NU in my notation. Generate a shared key. Here you see where this comes in, right? So the rockstar then sends over the TU and generates an HMAC, which is shared key and this request data. And in a redemption phase for the ferry, what happens is that the server again recalculates the request data, like it sees the request coming in, checks TU on its double spend list because it has a list which is kind of long, and then checks, calculates again big TU because it knows the hash function, signs that, and can then calculate the shared key as well. While doing so, and then this is where the signature comes in, and then it checks actually the HMAC, and if that works, then it knows, okay, this user issued this tokens, and this token is yet not spent, so it can just store the TU value to prevent double spending and send provide actually the service. Yay! So this is kind of the whole idea behind it, but this is still not the full specification. Just so you know, there is just to in this talk to make it a little more comprehensible. I just wrote hash function, but actually it's 3 hash functions used. So we have one hash function for the issuance phase, another hash function for the redemption phase, and a third hash function for the D-like proof inside the D-like proof. Just think of it, yeah, as a Schnorr construction. Yes, and then obviously, like also there is, we have some public data which is first shared to everyone. To then calculate also in the D-like proof, we have to make sure like which we say, oh, I signed this to something. Like we have to, the equivalence has to be kind of made. But you can have a look at the specification. I'm sharing the links in the slide later. But just to give you an idea, it's not. This is kind of the idea. It's not a crazy thing, and you can absolutely use that for your use case and your application. And this is what this talk is actually trying to tell you in its whole. Okay, this is the idea. And there's even code. This is what I wanted to tell you as well. So you can absolutely have a look at our code on ZKAPs. So what we do is actually, there's just Python bindings on the privacy pass library. So we just use another privacy pass library and change that to for our system. And here I just wanted to show you how it actually looks like. So this is, yeah, it's just, yeah, we actually call these things. So thanks a lot. And this slide is empty because we wanted to see your applications, your extensions, where you use ZKAPs or access passes for your use case. So happy to see those. And these are the links and references. Slides are shared. And if you have any questions, please reach out. We are happy to help, happy to answer questions. There's my email address, but there's also the Twitter profile of Least Authority, and everybody at Least Authority is very excited about this and happy to help, I think. Yeah, so please reach out, and if you have any questions, let us know. Thanks for watching this talk again, and bye-bye.